Welcome. Hopefully lunch is digested. You've had an afternoon coffee, sort of perk yourself up for the last, home stretch here of the afternoon. My name is Stephen Chambers. I'm on the Member API Foundations team at Netflix, and I'm going to be talking about some GraphQL performance issues and optimizations that we had at the scale that Netflix operates at. So let's get into it. So first, I need to provide some context, right? It's going to be difficult to truly understand, what these issues were, why we chose to solve them, without getting at least like a high-level understanding of our particular architecture. Then I'm going to walk through two journeys and performance optimizations that we had, one at the GraphQL gateway layer and one at the subgraph layer, or internally in Netflix, we refer to that as a domain graph service, or DGS. And then finally, how can this help you all? Obviously, our tech stack and architecture is ours. You have your own, business domains, your own sets of scale. I believe these two journeys have some key themes that can translate to, multiple different, domains and architectures. Now, obviously, we couldn't fly out the whole team to Amsterdam, and it's hard for 5 people to give, a talk, so I do want to give a shout out to some of my stunning colleagues back at home. So I am on the DGS side, I'm a member engineering, and Dan and Guanzong on my team were very involved in this optimization, as well as Tejas and Emily over on the GraphQL platform side. And that's the same team as Stephen and Mark, by the way, who I know are legends in the GraphQL community. All right, so let's set some context. We'll start with some fun with numbers, just to break the ice a bit. The number of slides in this presentation about GraphQL, 5%. You're all still here. That's fantastic. This talk is really about performance, but through a GraphQL lens, right? Most of us are familiar with GraphQL in some capacity, but in terms of how GraphQL operates at mind-numbing scale, that's what we kind of want to talk about today. What are some optimizations that we made to ensure that our systems are humming appropriately and that they can respond to requests with extremely high availability? So the number of Netflix pages on GraphQL. So this is a big thing for us. Over the last 5 years, we've been trying to increase this number over time. And a Netflix page is, in terms of the member experience, think of it as like a cohesive area of the app, right? If you load up the app, that might be the home page. If you search for a show, that might be a search page. If you click on a show, that might be the show's display page. And we have now 85% of those pages on GraphQL. That was probably 10 to 15 5 years ago. So we have been humming along trying to develop and get all of these things onto GraphQL as a platform. Now, near and dear to my heart, queries per second of our core DGSs, we're at about 1 million, which is really cool. Like, that's a lot of scale. Like, if you think about the field executions, like the actual resolvers that are running per second, 160 million. So think about that, like one Mississippi, 160 million resolvers just fired, a bunch of independent pieces of code that need to be tested, maintained. We can't have it go down. So that's truly what gets me excited to come into work every day, to develop at scale of that magnitude. And then when you think of the number of developers that are contributing to our system, we have over 1,000, right? So you think about there are 160 million resolvers firing every second. You have 1,000 people contributing to the code base. So it truly puts an onus on resilience and ensuring that our systems are performant and optimized. So now if we take a step back and look at the high-level federated architecture at Netflix, we have on the left side here all of our client-side platforms. So we have iOS clients, Android clients, TV, et cetera. And those all call into a GraphQL gateway, which is written in Kotlin. That gateway then fans out to the DGS tier, and that's where my team comes in on the member side. And then the DGS tier then fans out to the distributed system at large in Netflix. And that could be a variety of different protocols, gRPC, REST, et cetera. So pretty standard from a GraphQL perspective. And then on the consumer edge, because we have multiple edges, there are different groupings of DGSs, right? So there are DGSs for games. There are DGSs for commerce, like in pricing, account management. There are DGSs for playback. This particular talk is going to focus on the discovery experience. And the system that I'm going to talk about today is called DEP, which stands for the Discovery Experience Paved Path. So what is discovery? It's basically the systems that enable users to discover our content at Netflix, right? So if you, our goal is to ensure that you find a show that you want to watch. So we are basically from anywhere from when you boot up the app to when you actually decide to start playback on a show. And that could come in a variety of different ways, right? So on the right side here, there's an example of a home page, which I'm sure you're all familiar with and have seen. There's a details page if you want to look at a particular show, look at its seasons, shows similar to it, et cetera. And then there could be a search page. So if you want to search for a particular show. So DEP as a system is a system that we developed at Netflix on GraphQL, and it's server-driven UI. So the first question is, that is an incredibly vague term, like what is the server driving, what is server-driven UI? So the way we approach this problem is first our pages are split into a hierarchy where there's a top-level page, right? And the page is comprised of sections. And the sections are comprised of entities. Now, instead of granularly deciding on the server in terms of like a server-side rendering, we decide to provide signals to the clients. So if a client says, hey, what kind of section is this on the page? We might say from a server-side perspective, this is a carousel section. So render it as such. And a carousel for us is the user is able to swipe it to the right, which I'm sure all of you have done on the Netflix homepage. You might also notice that these entities look different, right? So how should I render these particular entities? We might provide signals saying, hey, this is a tall panel entity treatment. And at the bottom, this is a box shot entity treatment. So render it like a box, right? And this gives us the flexibility on the server side to be able to swap out these signals and create new user experiences without coupling ourselves to the client release cycle. So I know that was a lot of context, but to recap, Netflix operates at 1 million RPS of scale at the DGS layer. This particular talk is going to focus on the discovery experience. And the main system that we pushed was DEP, which is a server-driven UI system which provides rendering signals at the page section entity levels. Cool? All right. Let's get into the gateway optimization piece. So if we dive into the Netflix architecture a little deeper now, we were at the top level. Now, when it comes to my team, we maintained 2 DGSs. One was responsible for creating the page skeleton, and one was responsible for hydrating the particular page. So if we look at the page skeleton, what is a page skeleton? It's a 2-dimensional list of what we call entities. And the entities have the signals that I talked about earlier attached to them as metadata. So if you picture the Netflix homepage, right, it is a 2-dimensional list of IDs, more or less, right? You have lists of these categories of shows that we want you to watch, and then you have a list within each category for the actual shows, themselves. We are attaching, treatment data to all of those to give the UI signals on how to render that particular section or entity. So in this case, on the home page, we have a billboard as the first item, right? So this is the item that we think you're most likely to watch. And we're going to tell the client, hey, this is a single item section, and render this as a billboard. Now on the server side, if we decided to swap that out later, instead of a single item section, maybe we swap that out and there was a carousel section or something like that. If we wanted to promote, Netflix games, we would have the ability to do so without any, client-side involvement. But if you loaded up your Netflix app and there was just a 2-dimensional list of IDs, and you're like, hey, honey, do you want to watch, 4576 or 7829 tonight? That wouldn't be a great user experience. So then we have to hydrate the page. So this is taking that 2-dimensional list of IDs, that page skeleton, and enriching it with personalized assets. So a trailer maybe for the billboard. There might be some text, some images, some box shots to allow you to click on the particular show. So in terms of how clients are querying this system, they obviously query it in a hierarchical manner, right? So they start with, hey, I'm going to query for a home page, then I'm going to grab some sections, and then if it's a single item section, use this fragment spread. If it's a entity collection section, use this fragment spread. It's a tiny bit more complicated than practice, but I sort of redacted some of this stuff to, for ease of readability. And on the right here, you can see an explosion of different fragments. And that's because this is a server-driven system. So the client, in order to build a flexible rendering engine to be able to render any signals that we give it, they kind of need a fragment per signal, right? So if this particular treatment shows up, I want to render it in this way, and I need these fields. If this shows up, I want to render it this way in these fields. So what was the problem? So we have this new server-driven system, right? We rolled it out on an A/B test, allocated 15 million users to it, and then we get this lovely message from my colleague David, and he's like, "Hey, Steven, there was a large allocation of this A/B test, and we own the service that renders images at Netflix, and our traffic tripled." So 15 million users. We didn't even roll it out to the full fleet of 200, 300 million users. Just 15 million, and the traffic tripled. So not fantastic. We need to figure out why that is, because we expected it to more or less be a one-to-one migration in terms of systemic performance. We also noticed on the left here, you'll see that black line above the red one is our server costs over expected. So this A/B test was directly correlating to an increase in the cost of our EC2 instances. So why did that happen? When you look at the gateway query planning layer, like I mentioned earlier, we have these signals that we're providing to the client, right? So what the gateway was doing was for every unique set of signals, that was actually a different batch to the hydration DGS. So clients are issuing this query. We go to the skeleton DGS that I mentioned earlier. We call whatever services. We get that skeleton back. And then for every unique set of signals, so let's say there's a carousel and a box shot, and we want artwork. And then there's a single item section and a billboard treatment, and we want artwork. Even though those requests are independent and could be batched together, the gateway, because they were unique paths, exploded them out. So what we ended up having was a 13x fan out from the gateway to this DGS. So before, what was one call was now 13. Now, is this a problem? The number of entities that we're trying to render remains the same. It's really like a different batching paradigm. But for us, we noticed a hit to, number one, resilience, because networks are inherently unreliable. And the more calls you make, the more chance that you have for retries, the more chance you have for errors. And we also noticed that the RPS was increasing the cost of our particular services, because there's a lot of overhead to responding to a network request, right? So how do we solve this particular problem? So Emily on the GraphQL platform team came up with this particular fix, where if we look at a query plan on the left here, we have a sequence node, and first we fetch from the skeleton DGS. That makes sense. You can't really have a page without the page skeleton, right? Then if the query node had a parallel block with a bunch of these flattens in it for different paths, we were able to condense all of those flattened nodes into one fetch node with all of the paths within it. So what does that look like in practice? So there's a fetch node to hydration DGS, and during the skeleton query, there's a bunch of different merge paths, right? And the example that I'm showing here is a fan out factor of 2, just because it's easier to read, but you could envision this as a fan out of 13 on the average case. So what the query pointer is going to do is it's going to have a prefix for all of the entities queries coming up, as well as a merge path for where to fetch the representations. Then on the query side to the actual DGS, it will look something like this. So instead of 13 separate queries that are all entities calls, you will have one with aliases attached, where let's say the first one will have a prefix of sub-0, and then the query pointer knows, okay, for this merge path, for these sub-0 representations, I need to dip into this merge path, grab those entities. Again, another entities query, prefix with sub-1. For this merge path, I need to grab these particular entities so that I can find and send the sub-1 representations along. Now, is this the most optimal way to solve this problem? No, it's a bit hacky. There is going to be a talk actually next year. Emily and Mark are in the process of rewriting our query planning gateway at Netflix, so look forward to that next year. But this really got us through the fire, right? Because we had already developed this system, we rolled it out with some users, and it was something that we needed to fix imminently. So moving into the results of this particular fix, we had a 40% decrease in per instance RPS. We had a 4% decrease in per instance CPU percentage, and an 11% decrease in fleet cost just at the API layer. Obviously, that doesn't count all of our downstreams beneath us. So it was something that at least had us at parity for our migration, and it allowed us to roll out the rest of that system smoothly. Now, if we look at the subgraph side, so at a company like Netflix, it's tough to find operational wins at scale. Maybe you get a 5% win here, a 7% win there, but this particular optimization actually doubled the efficiency of our entire fleet. So a 100% increase in performance. It was really cool to see that. Like it's hard to find a optimization of that magnitude. And I think you'll be surprised by the code that was related to that particular issue. So how did we find it? Like every great problem and solution, it started with a page at 4 in the morning. So if you look at the blue lines here, the blue lines are successful RPS to our service, and the purple line is the service throttling. And Netflix prides itself on availability. Obviously, this purple line is not what we want to see, right? This is in the early days of our system. There's not a tremendous amount of traffic yet, but it was something that we noticed and wanted to dive deeper in to figure out how to solve it. So if you have a service that is throttling at 4 in the morning, the next step is maybe let's check your downstreams, right? Maybe it's a particular downstream that is responsible for this slowdown of your service, right? But when we looked at that, we realized that the deadline exceeded to our downstreams was sort of happening everywhere, which sort of points to something at the client side. And lo and behold, there was a massive stop the world garbage collection at the same time, which caused us to not respond to any requests. So let's try to figure out where is that garbage coming from. So this is an internal tool called Flame Commander, and it's a way to view the amount of time that the app is taking on its CPU cycles. And you can see here on the right side that 25% of our app, on average, was being spent collecting garbage. Now, obviously, the core goal of our app is to serve and respond to customer traffic. It is not a sanitation worker. It should not be collecting garbage 25% of its time, right? So we need to figure out where this is coming from. So the shocking culprit, if we look at this graph, was data fetching selection set impl get fields, which is actually a GraphQL Java API for introspection that I'm sure all of you are somewhat familiar with. And I think this is the key point in the talk that I want to iterate and reiterate. This is simple code. This is innocuous. Like, no one would look at this particular introspection API and be like, gee, I could go in here and double the efficiency of this DGS and get the promotion I've been looking for, right? Return data fetching environment, get selection set, get the fields, stream it, map reduce, done. So if we look into that GraphQL Java API in more detail, and this is very, very deep within GraphQL Java now. There's this method named compute values lazily, and there's these two hash data structures. There's a hash set and a hash map, and then there's this depth first search that starts at line 168 there. And if we look at that depth first search, GraphQL Java is basically executing the AST, doing a depth first search through the entire thing, and adding strings to these particular hash sets and hash maps. So why is that a problem for our particular system? This seems like fine. That seems like a reasonable thing for the library to do. So our system, because it is using server-driven UI, it has two things going on. Number one, there's a deep nesting. So the tree is deep, right? There's home page, sections, edges, node, entities. You might have some buttons on there. So the tree is very tall. And also, because of our explosion of fragments, the tree is also very wide, right? So if we look at this problem, visually, we have this tall, wide tree. And for us, all we really want to do in this code is to grab the version off of the sections node, which is highlighted in yellow there. So what GraphQL Java is going to do is it's going to do a depth first search through our entire tree, add these strings to various hash sets and hash maps that I mentioned, and you can see very clearly where this memory is coming from, right? And also like how it's not necessary for our particular use case. All we want is the version on the particular sections node. We don't need to traverse the entire tree. So in terms of solving it, instead of doing that depth first search, we just did an easy breadth first search because we knew what the depth was. And we implemented something custom so that instead of relying on this library that was adding to all of these hash data structures, we simply did our own BFS through the tree, found the node, grabbed the version, and moved on. So in terms of the results, we had a 40% improvement in JVM allocation and promotion rate, which is nuts. And also, I love this graph. For the same amount of work, so the blue lines are RPS, right? And the orange line is CPU utilization of the service. So after rolling out this fix, for the same amount of work, our CPU utilization basically cut in half. For something as innocuous as just calling a getFields API in GraphQL Java, right? So how can this help you, right? GraphQL at scale is the first sort of tentpole I want to talk about here, where at 1 million RPS, every edge case is really just a matter of time. Frameworks and tools have to solve for the generic by definition, and I think that's important. Like, GraphQL Java, in terms of adding to those hash data structures, wasn't inherently a problem, right? Like, they weren't doing anything wrong. It's not like we are going to make a contribution to GraphQL Java to not do that. It was just wrong for our particular use case and our particular scale. So even though GraphQL does, work for the system that we developed, it wasn't really a natural fit for what we were trying to do. But I don't think a natural fit really exists, in the industry today for, server-driven UI systems. It's a relatively, new thing. But we were able to make it work through these improvements and these sort of tangential optimizations on top of the framework itself. In terms of communication, I think the communication between the GraphQL platform team, which owns the gateway, and the DGS side was excellent. Especially during the GraphQL, when we had the gateway optimization. And we were, sort of freaking out, people being like, hey, our traffic's tripling, like we need a fix like right now, like we have a bunch of people that are waiting on this system. And they smartly were like, hey, change in batching paradigm isn't necessarily bad, right? If you could provide us data, like pure empirical data that says, hey, this cost increase is directly attributed to this particular fan out, then yes, we can prioritize it, but we have, a ton to do. And once we provided that data, they were able to, reprioritize things and get us in, that tactical fix so that we could roll out our system. From the Subgraph side, the optimization really took the entire team. That particular piece of code, like I mentioned earlier, that's really tough to find, right? Like it's adding to a hash set in a dependency, a few layers down from your app. It's really, really hard to find that particular issue. And it took our entire team through, on-call handoffs, communicating with the GraphQL Java folks on GitHub, them being like, man, your queries are really, really large. And then, the eventual implementation to get us through, on our side. And then finally, tooling and resilience. At this scale, resilience is like brushing your teeth. You have to do it every day. Otherwise, it's going to turn into a snowball that gets too big to manage. And even innocuous code, like simple code, like I mentioned earlier, can host massive efficiency bottlenecks. So in order to find those efficiency bottlenecks, tooling is super, super important. We would not have ever found the bug if not for our friends at observability and resilience engineering to provide us these tools to allow us to look at time series data, to look at CPU, to look at heat maps on particular time ranges. So my call to you all is if you are going to operate GraphQL at the scale that Netflix has, ensure that those systems and tools exist, right? Maybe have a pre-mortem before you roll out your system. Like, hey, if something went wrong, if I got paged at 4 in the morning for throttling, what would I do? Like, what would be my next step? Do I have the data and the tools needed to solve that particular problem? And with that, that is the end of my talk today. Thank you very much, and I'm happy to take any questions from the crowd. Any questions? Go ahead. Yeah, that's a good question. So in terms of, I think DFS versus BFS was like a micro optimization, right? Because if you do know the depth ahead of time, like software engineering 101, you know that it's the depth 3. You could do a depth first search, to depth 3, but you might go down, the left node a bit too much and then come back up and then find your particular node. I think for us, it was really less about DFS versus BFS and more about not traversing the entire tree beforehand. Because what was happening was when we were doing that introspection and we were calling the getFields API, it would traverse our extremely deep tree and our extremely wide tree and add a bunch of strings to a bunch of data structures that we didn't actually need, right? So we could have implemented a depth first search and stopped at depth 3 and not added those strings to the various data structures like GraphQL Java was using, and probably encountered similar improvements. But the BFS was more like a micro optimization because we knew with our schema structure this is going to be a depth 3 for sure. So this is it's going to be easier to traverse level by level versus going too deep into the query and coming back up. Any other questions? Yeah, so the question was, I talked about, STUI, GraphQL, wasn't really a natural fit for it. Do we have any follow-ups? It's something that we're still trying to figure out as a company. Right now, we have 2 different groups that are developing server-driven UI systems. Ours, and the member side, is more signaled because by definition, the member experience tends to be rich, right? So we want to give more powers to our developer to use those signals in ways that make sense for them. Where maybe on the commerce side, their server-driven systems may be more granular because they want to say, hey, this is a upsell. We're trying to get you to upgrade your plan to 4K or something like that. It's not really a rich experience. It can be server-side rendered. We are working on trying to figure out how to scale server-driven UI with GraphQL because obviously the more signals that we add, the deeper and wider that tree is going to get. There are some things we're talking about internally about, maybe doing, contributing to the spec, adding something like a scalar for an SDY system, where you can basically have a point in your query structure, but you can say, hey, everything from here on out is created by a server-driven system, and you're losing the GraphQL flexibility. But you can, use GraphQL throughout the rest of the query structure. So it's something that we don't quite have an answer to yet, but I don't think there's really an answer to server-driven UI in the industry. Like, there's not some API tool that's like, oh, we would definitely use this. Any other questions? All right. Well, thank you very much, and enjoy the rest of the talks.